inviting me to this nice symposium. Actually, I got my PhD degree from chemical engineering in 2002 under the supervision of Professor Hong Lee. But I'm currently working at Mechanical Engineering Department, Seoul National University. Well, let me first point out that this is quite an ongoing project, so there is still a long way to go. So I think I can present a more complete version of this work next time. So, also, apparently, this work has less to do with organic transistor, but I think the same approach can be equally applied to flexible organic display. Well, today my focus is on SDB. As you know, SDB products are everywhere in our daily life, from camcorder, high resolution television, laptop computer, and mobile phones or personal displays. Well, I think this industry has made incredible advancement during the last few decades. So I think there's no doubt that as the industry will be the mainstay in our economy. Basically, this LCD module consists of 3 units. One is backlight unit at bottom, and another is TFT, amorphous silicon transistor unit, and the last is black matrix color filter unit at top. So of course, my interest is on black matrix pattern on the top layer. Well, in order to make these color filters, in order for high performance of color filters, we need a black matrix here. Basically, black matrix blocks out the transmitted light up to 99%, 9999%. It's quite 100%. So the basic optical density is larger than 3.5. It's very quite high. So the operation is very simple. As you know, RGB is the 3 major components of full color display. So we can generate a certain color by a combination of these 3 colors. So here, well, there are basically 2 materials for black matrix. One is metal, such as chromium, or the other is polymer resin. So because polymer is intrinsically transparent, for thin film, we need to add some black carbon black particles to obtain a high optical density. So, well, I heard that people in LCD, TFT people say that they're not sure about which will be taking up the leading role in a flexible display. Some people say it's organic transistor, or some people say it's still TFT. Because a recent article, I saw a recent article published in Nature very recently that they reported that the amorphous silicon can be printable even at low temperature. But that means the amorphous silicon transistor can be made on plastic substrate possibly. So I believe that this flexible industry will be very competitive in the coming years. As you know, in order to fabricate black matrix patterns and color filters, photolithography is widely used. Basically, there are 4 masks are necessary to fabricate, complete the full step. And each photolithography step consists of several procedures, such as coating, UV exposure, developing, and post-baking. So total step will be quite many. So interest here is that how can we reduce the number of steps using unconventional lithography and possibly with inkjet printing. That will significantly reduce the time and cost in black matrix fabrication. So for lithography, it's very well established. It has been studied over 100 years, so it's very well established. But however, it is also an expensive process. It involves multi-steps, multi-masks, and alignment, and expensive materials and equipment. I think for lithography, it is fast approaching the cost limit imposed by the market. So there is a tremendous competition among the industries. How can we reduce time and cost by replacing the current for lithography? So our solution is very simple. A new patterning strategy is highly in demand. So can you imagine any other solutions to replace for lithography? There are many techniques. So basically, so-called contact-based lithographies possibly replace non-contact-based for lithography. There are tons of papers in the literature regarding these contact-based unconventional lithography, such as non-imprinting lithography, soft lithography, capillary lithography, or micro-contact printing, so on. It's quite many. My focus is on capillary lithography here. So a typical procedure is like this. This is molding case. First, a pattern mold is necessary. So every unconventional contact-based lithography utilizes the direct contact between the mold and thin polymer film. So a pattern mold is necessary. So this mold is placed on top of a thin polymer film. Then this process induces the deformation of a thin polymer film into the mold cavities by using different physical forces. So sometimes we need to increase the temperature, or we need to apply the UV exposure. So any type of solidification is necessary here. After peeling off the mold, we can fabricate a negative replica of the mold, master mold. So for further pattern transfer, people use wet or dry etching, or sometimes litho process to use here. So I think this kind of contact-based lithography is not new. It's basically it dates back to the early 11th century. So as you learn from the history textbook, the first printing masterpiece called Dictation was invented in our country. So it precedes that of Germany by more than 200 years. So I think that's why I think our Korean people have inherent aptitude for this kind of contact-based lithography. Trust me. I think they do that. So our strategy is very simple. How can we induce the deformation of polymer film by applying different physical forces? So first method is basically molding by heat. So we coined the term capillary lithography, which means we are doing the lithography based on capillary forces. Capillary force is very weak force that macroscopic work. You can easily spill the coffee in your cup by putting your cup upside down. It's very easy. But however, it is very difficult to remove a small droplet confined within a small tube. You cannot easily remove the drop, right? So this capillary force is the dominant force in micro nanoscale. It's quite high. So our method is like this. So once we use electric mold like PDMS, then we apply the mold on top of spin-coated polymer, and then we raise the temperature above the polymer glass transition. Then initially, immobile polymer film spontaneously rises into the cavity of the mold by capillary action. And then after cooling down and molding over, we can fabricate a negative replica of the mold. Interestingly, there are two limiting cases. If the polymer film is very thin with respect to the height of the mold, the substrate surface can be almost exposed. In this case, a meniscus is observed, like here, which indicates that this process is driven by capillary force. So in many cases, it is very, very, very important to expose the surface surface in one step. Otherwise, we need to apply additional dry or etching step to expose the windows. So our interest here is how we can expose the surface in one step, hopefully on large areas. So that's our major goal. So we can fabricate various micro nanostructures. Sometimes three-dimensional structures are doable. So for thin film, you can see a meniscus here, which is signature mark of capillary rise. So another way to induce capillary rise is just use a solubilized wet film having a solvent, high amount of solvent. So when the polymer solution is liquid and the PMS mold is directly applied, this polymer can spontaneously fill up the void spaces, and then we can find the negative replica after molding over. This is very simple. Basically, you can apply to every polymer as long as the polymer is solubilized in certain type of solvent. Another advantage is that the viscosity is very small due to the presence of solvent, which is a very big advantage in terms of a large area process. So these are some examples of this method. So the last, another way is to utilize UV exposure, because PMS mold is transparent. After putting the mold on top of the surface and expose the surface upon the UV, we can fabricate the same type of negative replica, basically the same. In this case, we are using a low viscosity UV curable resin. So there's no solvent involved. So generally, basically, we can fabricate, various micro nanostructures in one step. So some papers are impressed here. Well, these are three methods we want to apply for fabricating black matrix patterns. But here is the point. So one of the big challenges in black matrix fabrication is that we need to expose quite a large portion of surface surface in one step. So the black matrix patterns are like this. A relatively large portion of the substrate should be exposed. That means that we need to fill a very thin layer of these lines. So this is called low duty ratio pattern. How can we overcome these problems? By using this contact-based technology. So as you may know, Professor Lee proposed a very nice concept by combining molding and dewetting, as shown here. So it's very difficult to expose the large portion of substrate in one step. It's very difficult by molding itself. So this paper proposed a nice concept using pre-patterning followed by dewetting of low viscous polymer, so that this kind of nice patterns can be fabricated. So I think this process is still a two-step process. So let me present a little bit improved version of capillary technology. So my interest is here, how can you fabricate blend patterns in one step? So first we checked the patterns made by photolithography. Of course, the patterns are very beautiful. Very great. No defects or any dysfunctions were observed. From this image, the height is about 1.5 micrometer, and the glass substrate. Typically, Pyrex glass is used. The surface is almost exposed. So, from optical image, blend matrix patterns are, it's black. It's quite black. And then the exposed surface is white. So these are typical images made by photolithography. So again, our goal is one-step fabrication of blend matrix patterns without residual layer over large areas. Because it's quite challenging to me, because the pattern is quite it's not easy to deal with. The low-duty patterning, and also the direct exposure of the subsurface is quite difficult. So we attempted to use three methods here. One is microcontact printing, and the other is solvent-assisted capillary lithography, and finally we applied UV-assisted capillary lithography. Other methods are also available, but we only tested three methods. We first tried microcontact printing using PDMS mold. So actually, we expected that this layer would be directly transferred to the glass substrate, but however, this layer was not directly transferred. Instead, it moves into the cavities of the mold, so that exactly the opposite behavior was observed. So basically, we observed three kinds of phenomena here. Some region was okay, but we found a mixed morphology of molding and degrading. So I think that microcontact printing is not suitable in this process. So next, we tried solvent-assisted capillary lithography, the so-called soft molding technique. In this process, a thin layer of PL film is spin-coated. And before solvent evaporation, we directly place the PDMS mold on top of the surface, and then this polymer spontaneously fills up the cavities by capillary action. So apparently, the pattern result was very nice, but for some regions, we observed the mixed morphologies. This region is okay, but for some region, the polymer did not fill up the void spaces. Also, at the region, the capillary body was not complete. So I think this behavior can be attributed to some complex behavior of solvent, because it's very difficult to control the metallability of solvent with PDMS surface and the solvent surface as well. It is very difficult to do that. So to overcome, so this 3D profile images show that there is some residual layer remaining. Because I think this region, the solvent quickly evaporates during the molding process, so that this region was not mobile after putting the mold. So the variance was not reasonable, but some non-uniformity was observed here. So finally, we used UV-assisted capillary lithography. In this technique, we spin coat the UV curable resin. This basically low viscosity polymer, The viscosity is about 10 times that of water, very low viscosity polymer. After placing the PDMS mold, this polymer is also, spontaneously rising into void spaces. And then, surprisingly, the pattern result was very, very good. Large area process was also doable. So we fabricate the pattern over 4-inch glass wafer with minimal defect. So from 3D profile images, we found that the substrate surface was almost exposed, and the uniformity was quite good. But there is little non-uniformity across along this area. So, but I think at this moment this is okay. So, but from now on, let me talk about the inkjet printing of RGB arrays. Initially, I intended to present full color displays, but due to some unforeseen circumstances, here I'm going to present only one color printing. Here. Basically, we used UV chrome resin here. The pattern was okay, and then we deposit green power filter using inkjet printing. So I think we have still a long way to go, but I think the printing of the other two colors would be basically the same. Well, if this process is successful, the over step is very short. So only one, I think only one step is necessary. Or hopefully, mask is not necessary. So we are still currently working on this topic with some with a major display company. So it's basically the same with the previous one. So let me briefly summarize our results. There are some challenges in volumetric fabrication using contact-based technology. So one is, of course, large area patterning. And the second is uniformity control. For defect control is also difficult. And the digital layer should be completely removed, hopefully, or additional etching or etching step is needed. Also, productivity should be addressed. Right now, our material is not optimized material. It's basically transparent. So I think we need to combine our low viscous resin with carbon black mill so that high optical density can be ensured. Still, we are working on that as well. This work, yeah, technology. It's very kind.